Materials supplied by Microsoft Corporation may be used for internal review, analysis, or research only. Any editing, reproduction, publication, rebroadcast, public showing, internet, or public display is forbidden and may violate copyright law.
Okay, hi everyone. So my talk is going to be about Frank-Wolfe Bayesian quadrature, probabilistic integration with theoretical guarantees. And this is joint work with Chris Oates in Sydney, Mark Girolami, who's my supervisor at Warwick, and Mike Osborne from Oxford. Okay, so why should you actually care about the method? Well, as was described by Zubin Garamani earlier, probabilistic inference is one of the main topics in machine learning, and in this case, you have to do integration all the time. So for example, if you do marginalization, conditioning, then these are all integrals. And in most cases, they're not actually going to be analytical, and you're going to have to use some kind of numerical scheme. So a typical way of approximating integrals is using quadrature rules. So you approximate your exact integral, which is here on the left, with a weighted combination of function values. And you have to pick some points, the x's, and some weights, the w's. Now, this is usually very, very slow. And well, of course, it depends on the method. But what I mean by slow is like your error between the exact integral and the approximation decreases very slowly in n. And so, for example, if you take Monte Carlo methods, then you're going to sample some x's from P, and then you're going to weight them all equally. And this will converge as n to the minus 1/2. And in a lot of cases, it's going to be way too slow, and you might not be able to afford taking a lot of samples. So one particular thing that you can do is use Bayesian quadrature. And in this case, the idea is to use some prior information you might have about your integrand to guide your choice of the design points and the weights. So what I mean by prior information is you might have some idea of how smooth your function is or other properties, and you can encode this directly into your numerical scheme. Now, okay, so this is a solution, but it's actually just moving the problem around because there's not actually any convergence guarantees for Bayesian quadrature for now, and so you don't know if it's actually worth using it. Well, that's actually why you'll want to go and check out the paper, because in this case, we showed that if you use a particular convex optimization algorithm called the Frank-Wolfe algorithm, then your Bayesian quadrature scheme can have exponential convergence under certain assumptions. And obviously, exponential is much, much faster than 1 over square root of n. And so you should definitely come and check it out. And it's poster 57. And there's also a whole workshop on Friday on probabilistic integration, which I invite you all to come. Thank you.
Hello, everyone. My name is Surush Shafizadeh Abode. I'm from EPFL. The title of my presentation is Distribution Robust Logistic Regression. This project is a joint work with Peyman Mahajan and Esfahani and Daniel Kuhn. Logistic regression is one of the most widely used classification techniques. In logistic regression, we aim to construct a classifier via maximum likelihood estimation. We also wish to quantify the classifier's risk. In both cases, we need to evaluate an integral with respect to the distribution P of feature label pairs. However, the distribution P is unknown and must be inferred from the set of training data. Classical logistic regression just replaces P with the empirical distribution P hat n on the training samples. However, this leads to overfitting. Our suggestion is to construct a set of all distribution that could have generated the training data with high confidence. We call this set as the ambiguity set. So the proposed distribution robust logistic regression model tries to find the minimizer of the worst case expected loss, where the worst case is taken over all the distribution in the ambiguity set. We also aim to quantify the best and worst misclassification probability over the ambiguity set. The challenge here is to construct an ambiguity set such that the resulting classifiers offers out-of-sample performance, and it leads to a tractable reformulation. In this study, we use we construct the ambiguity set as a ball in the space of probability distribution around the empirical distribution. We use the Wasserstein distance to quantify the distance between two distributions. More specifically, the Wasserstein distance is defined as the minimum transportation cost for moving the probability mass from the distribution P1 to P2. Our approach has several benefits. First, due to the recent measure concentration result, it offers out-of-sample guarantees. Second, it leads to a tractable program. And finally, we can find a probabilistic interpretation for well-known regularization technique. Also, as you can see in the figure, we consistently outperform the regularized logistic regression and classical model. Thanks for your attention.
Hello. My PhD advisor, Thorsten Joachims, and I studied how we can learn from the logs of interactive systems that only provide us bandit feedback. We identified an interesting new kind of overfitting in this setting, which we call propensity overfitting. Our conditional random field prototype that learns from bandit feedback, avoids this overfitting using the ideas from this paper, is available online. The formal setting is batch learning from bandit feedback. Imagine you have collected X, Y, delta triplets from your search system. X denotes the user queries, Y denotes the action that was taken by the system, so a ranking was shown, and delta denotes the user's feedback on the presented ranking. Typically, we don't know how the user would have reacted to some other possible ranking. This aspect of the logs is called bandit feedback. We want to use these logs to find a good policy H that can generate Y given X. Bandit feedback makes this problem harder than supervised learning, where we are told the best possible action on the training set. It's easier than reinforcement learning, where we also have to solve credit assignment. And it's not quite online learning for contextual bandits, because there is no trade-off between exploration versus exploitation going on here. This is a very practical problem. We have collected terabytes of logs from search, from recommendation, from ad placement, and there is a general recipe for reusing the logs from these systems in a model-free manner. First, recognize that these logs are biased. If certain actions were preferred by the system, then those actions would be overrepresented in the logs. So use importance sampling to debias them. Next, do empirical risk minimization, or ERM. This gives you training objectives very similar to supervised learning, a train error plus regularizer, except the training error is now this R hat that's computed via importance sampling. In practice, ERM with this R hat often fails. A common failure model is where ERM completely ignores the feedback that you've collected in the logs, just overfits to the propensity of seeing your data items in the logs, and finds a H that's very simple, whose empirical variance is going to be very small, and you think you're doing really good, but you're actually very, very wrong. No capacity control or variance control regularizers we have so far fix this issue. And the insight really is these R-hat estimators are subsequently getting used in an optimization problem. So what we really need is an estimator that works well with optimization. This R-hat is not one of those. We identify a particular property called equivariance, which allows for robust ERM, and we point out that the self-normalized estimator is indeed equivariant, and it's much better than this. Picking the best estimator for this problem is still an open question. But surprisingly, the self-normalized estimator runs very fast, taking just a few seconds to learn multi-label classifiers. Join me on number 59 for more.
My paper works on asynchronous parallel stochastic gradient for non-convex optimization. I'm Xiangru Lian, and my co-authors are Yijun Huang, Yuncheng Li, and Ji Liu. We're from University of Rochester. Non-convex optimization is quite common in applications such as deep learning, natural language processing, and recommendation system. And asynchronous parallelism is widely used in deep learning. Asynchronous parallelism has a favorable property that it can substantially reduce the idle time in synchronous parallelism because it does not need the synchronization step. Our paper provides some theoretical analysis for asynchronous stochastic gradient, especially for non-convex optimization. In asynchronous stochastic gradient, there is usually a central node keeping the optimization variable x, and there are many workers running traditional SGD algorithm independently and concurrently. The main difference from the standard SGD is that the x hat used to compute the stochastic gradient might not be the same as the current optimization variable x in the central node in asynchronous setting. This is also a key challenge in analysis. The other key challenge in analysis is that different implementations lead to different forms of x hat. For example, the x hat in cluster implementation and multi-core implementation are quite different. Our paper actually covers both implementations and shows that the asynchronous stochastic gradient, the convergence rate of it is consistent with stochastic gradient descent. And we show that a linear speedup can be achieved up to the order of square root of iteration number walkers. Here is an intuition of linear speedup. The deviation from the true gradient caused by SGD actually dominates the deviation caused by asynchrony. Thus, the asynchrony will not seriously affect the convergence rate. We thank all the reviewers for their constructive comments and welcome to our poster tonight. Our poster number is 63.
Good morning, everyone. So I'm Andre. I'm from Princeton. I'll be talking about a joint work with Pranjula Vasti, who's at Rutgers, about some cases where we can say something provable about variational inference as applied to topic models. Okay, so let me give you some context first. So in recent years, it's been getting increasingly more and more clear that most problems that you care about in machine learning tend to be non-convex in nature. And so to give you some sort of stereotypical examples here, it would be things like clustering, map, approximating posteriors, etc. So from a theoretical point of view, these ought to be intractable, but what happens often in practice is very simple local search or descent type of heuristics tend to work quite well. So what am I putting in this category? Well, it's things like EM, variational Bayes, backpropagation, other variants of gradient descent, etc. So the sort of very big question for theory here to answer is, why does this happen? So because of time and space constraints, vastly and egregiously kind of oversimplifying and omitting, let me just mention a few success stories where this has been done before. So this has been done for various variants of k-means. For example, in the case of mixtures of Gaussians, alternating minimization has been analyzed for matrix completion, for phase retrieval, for dictionary learning. And so with that in mind, I can tell you what we do. So we basically add one more heuristic to this list of things that we know how to analyze. And we analyze a version of mean field variational inference as applied to topic models. So the things that you need to know are the following. Our assumptions are very reasonable. They're similar to what prior theoretical works on topic models assume, but nota bene, these works do not actually use these local search or descent type of algorithms. Our initializations are also reasonable. In fact, they're inspired by what we think people use in LDAC, which is the most, probably the most often used software for doing variational inference for LDA. And our proof methods are somewhat different from these other sort of prior works that I mentioned, so hopefully there'll be some other applications of them. So please come to the poster. It's not, the number is not on the slides, but it's 48. Please come to the poster to hear more.
Hello everyone, my name is Igor Collin and I'm here to talk about extending gossip algorithms to distributed estimation of few statistics. This is joint work with Aurélien Bellet from INRIA Lille and my advisors Joseph Salmon and Stéphane Clémençon from Telecom Paris. Let's consider the problem where some observation sample is distributed over a connected network. Nodes of the network can be smartphones, sensors, what you want. And you want to estimate a pairwise mean statistics, for instance, variance, area under the ROC curve, or any pairwise statistics involved in a machine learning problem. What we want here is an algorithm that can perform in an asynchronous setting with respect to some communication and local storage constraints. This problem is fairly typical in domains such as telecommunications or sensor networks. We based our approach on gossip protocols. That means that at each iteration, only one edge is activated. This protocol has been widely studied for estimating the sample mean. In this case, selected nodes just average their estimates. However, naively extending such algorithms would lead to massive data transfer in the case of pairwise estimation. Our solution consists in the following. Each node stores 3 elements: its own observation x, an auxiliary observation y, initialized to x, and its statistic estimates h hat. At every step, selected nodes average their estimates, as in the standard mean estimation. Then they update their estimates using the 2 observations they hold. And finally, they swap their auxiliary observation. This algorithm can perform in a fully asynchronous setting and is shown to have a theoretical convergence rate of 1/t with an explicit dependence in the spectral gap of the network, which is a measure of communication capability of a network. It also shows good practical performance in simulations. Thank you for your attention, and I'm looking forward to seeing you at poster 72 tonight.
Hi everyone, I'm Bahran Mirza Soleiman, and this is a joint work with Amin Karbasi, Ashwin Madani-Diuro, and Andreas Krause on distributed submodular cover problem. Suppose that you have a large data set and you want to find a subset, ideally as small as possible, that achieves the desired quality Q according to a utility function. In many applications, such as clustering, recommendations, document and corpus summarization, and nonparametric learning, this utility function is monotone submodular, which means that adding an element to a smaller subset helps at least as much as adding the same element to a larger subset. For monotone submodular functions, the greedy algorithm that iteratively selects the best element achieves a logarithmic approximation guarantee for this NP-hard problem. But for large data sets, the greedy algorithm may be impractical. For example, if the dataset is not even fit on the memory of a single machine. In this work, we propose the first distributed algorithm for submodular cover problem, where the dataset is partitioned on a set of m machines operating independently. The key idea is a reduction to the problem of cardinality constraint submodular maximization, for which recently many distributed algorithms have been proposed. A technicality of our approach is to estimate the size of the optimal solution while coordinating different algorithms and sharing partial solutions between consecutive rounds. We also provide approximation guarantees for our algorithm. In particular, we show that the solution quality in terms of the solution set size is competitive to that of the centralized greedy algorithm, while the number of rounds compared to a naive distributed version of the greedy algorithm improves from a linear dependence on the size of the optimal solution to only a logarithmic dependence on the optimal solution set size. We also applied an algorithm on large data sets. Here you can see the result for vertex cover problem on a network of 2 billion edges. Our algorithm has a trade-off parameter alpha. For smaller values of alpha, as you can see, we get very close to the result of the centralized greedy algorithm, which is shown as dashed line, but in much smaller number of rounds. Come to our poster number 65, and I will be happy to discuss this more. Thank you.
Hello, everyone. I'm Murat, and I'll be talking about Newton-Stein method.
So in this paper, we considered the problem of finding the maximum likelihood estimator in generalized linear models when the number of observations is much larger than the dimension of the parameter. So we minimize the negative log likelihood by standard iterative updates, but the goal is to find a scaling matrix Qt that is computationally efficient and also provides sufficient curvature information. So I'll give you the basic idea about Newton-Stein method. So we start writing out the hashing of the GLM problem, and we notice that it's just a sample mean estimator of its expectation, which is written on the right-hand side. And if we pose this as an estimation problem, we apply Stein's lemma and find an equivalent expression, which is written on the second line. And instead of estimating the expectation in the first line, we estimate what the Stein's lemma give us. So this algorithm takes a Newton step relying on a Stein-type lemma. So we call it Newton-Stein method. And just by using this equation, we can reduce the Newton's method order MP squared per iteration cost to order MP, which is just the cost of computing the gradient. So we show that this algorithm, the Newton-Stein method, gets a composite convergence rate, which is, it starts with a quadratic rate and then transitions into linear rate later on. This is also consistent with our experiments. As you can see that the initial convergence is quite fast and it transitions into linear near the true minimizer. So I'll talk more about the composite convergence rate and give you more experimental comparisons with other existing methods in the poster session. Thank you.
So this concludes this morning's session. Let's thank all the presenters once more.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.